A warm welcome. This is Control Systems course with lecture 2.2 representing the types of test inputs and the first and second order response. And next one is the impulse signal. Impulse signal, the best example for impulse signal is the lightning. It will be available only for a short duration, but its impact will be of large magnitude. That's the case. And simply saying the Laplace transform of the impulse function is unity. Mathematically, an impulse signal is the derivative of the step signal. And next one is the sinusoidal signal. Sinusoidal signal normally it will be varying with respect to time with the function of sine wave. We can see these are the representation of the signals graphically. You can see step signal is a constant value, ramp signal it is linearly increasing with respect to time, and when considering the parabolic signal it is increasing in the shape of a parabola, that is in terms of square. And impulse signal at t is equal to 0 it will be of very large magnitude, and after that its value is equal to 0. This is what is called impulse signal. Normally, by taking the Laplace transform of these signals, a becomes a by s, at becomes a by s square, at square by 2 becomes a by s cube, and the impulse signal value will be equal to 1. The exponential term is of minus value. I mean, it is decreasing, but it is 1 minus the decreasing value. So automatically, since this is decreasing, C of t will be an increasing one, because 1 minus decreasing value will automatically increase the value. So if we are giving a step input to a first order system, then obviously the system will provide an exponential output which is increasing, and it will reach the set point value. This is what is the time response of first order system with unit step input. So let us see about second order system. Here this is a simple block diagram, and this is our plant, and we have a feedback network here. So while you are taking C of s by R of s is equal to G of s divided by 1 plus G of s, the H of s, I mean the feedback is considered to be unity. And now let us substitute this value, we'll get an equation. This is a standard form of second order system. C of s by R of s is equal to omega n square divided by s square plus 2 zeta omega ns plus omega n square. This is the standard second order system equation. The denominator of the transfer function is called the characteristic equation. This denominator term is called characteristic equation. Here omega n is called damping ratio, and omega n is called undamped natural frequency, and zeta is called damping ratio. Now let us consider the characteristic equation. While this is a quadratic equation, upon solving we get two different roots, minus zeta omega n plus or minus omega n root of zeta square minus 1. So we have two different values of s here. So two roots of s are present. Now based upon the zeta value, that is based upon the damping, the roots of the characteristic equation can be considered to be, the roots are imaginary when it is an undamped system. Undamped in the sense zeta is 0, there is no damping. So when zeta is equal to 0, the roots becomes imaginary. Now we will prove it, right? Second, when zeta is equal to 1, when zeta is equal to 1 means it is critical damping, because the ratio, the damping ratio formula is, it is the ratio of critical damping to actual damping. So when both are equal, only then damping ratio will be equal to 1. So when actual damping reaches critical damping, we call the system as critically damped system. When zeta is equal to 1, at that time the two roots are real and equal. But when overdamping occurs, the roots are real but they are not equal. And also there are conditions when the system is underdamped, that is when sufficient damping is not provided, then the two roots become complex conjugate roots. In the sense, oscillations will be there. There is no suppression of oscillation, so continuous oscillation will be there. Second, for underdamped system, zeta value will be between 0 and 1. So let us take the transfer function. Take the characteristic equation, split the equation, you will get the terms. So you are having two values here, and then you can apply R of s is equal to 1 by s, apply it, apply the partial fraction, you will have this. On solving, we'll get again the roots. So now we have three different values here, and taking C of t, inverse Laplace transform, we can achieve 1 minus the exponential value, cosine value, here the exponential value and the sine value. Now, as time goes on, when time is increasing, this value will be getting reduced as well as this value will be getting reduced. So, when both the cosine wave and the sine wave gets reduced, normally the C of t will be trying to reach the value 1. Hence, this is the case. Here, we can see that initially there are oscillations, but when time goes on, the oscillation is getting damped and it is going to reach the stated output. This is what is the response of underdamped second order critically damped system. While considering critically damped system, zeta is equal to 1. At that time, we can see two roots are there. Both the roots are same. S plus omega n is the term. And apply the partial fraction and we'll get this equation. So in this case, it is purely exponential. It is not at all based on sinusoidal value or cosine value. It's purely exponential at time. So as time goes on, it will exactly reach the, there is no oscillation here. It's an exponentially rising one. Rises and reach the stated output. Next is the overdamped system. In overdamped system, zeta is greater than 1. So what we are going to do is we have to realign the system such that we get zeta square minus 1. In this sense, you have to rearrange the system, and then we have to consider the same pattern. You have to substitute R of s is equal to 1 by s, apply partial fraction, and then we'll get the output C of t. Here, as damping increases, that is when overdamping is being occurring, the oscillations, no oscillations will be present because we are overdamping the system. But what is the case is, you can see when zeta is equal to 1.5, it is reaching the value of 1. When zeta is equal to 2, it is not getting reached to the desired value. It is getting, the value is less. When zeta is equal to 3, the value is becoming much more lesser. Even though there is no oscillation, overdamping will not make the system to reach the desired output. It will suppress the output. This is what is the case of overdamped response.